I will introduce now our third speaker, Professor Guido Gerig, who is the director of the Utah Center for Neuroimage Analysis. He holds a faculty position at the Scientific Computing and Imaging Institute, also known as the SCI Institute in Salt Lake City, at the University of Utah, with adjunct appointments in biomedical engineering and psychiatry. Guido has led a large number of national and international projects with multidisciplinary collaboration between medicine, engineering, statistics, industry, and computer science. His current research topics are the analysis and modeling of the early developing brain, longitudinal analysis and multi-shape complexes, and also new methodologies for statistical analysis of white matter using diffusion tensor images. And many of the tools and methods he has developed are open source and are made available to public.
Okay, thank you very much, Nicolas, for this kind introduction. So as you heard, I will continue what you just heard at the end in this spatiotemporal domain to tell you a little bit more about what can be done and what should be looked at. So first of all, many thanks to the Collège de France and Nicolas Ayache to make that happen. And I was in particular struck by when I walked over the floor this morning, this motto, dos et omnia. I mean, everything is taught, even this high tech in medicine. So this is the operating room of the future, this time not in France. This is the Boston version at Harvard Medical School. But I think it's amazing that this high tech that we develop with math and fundamental technologies finally finds its way into the community, scientific community. So I will talk a little bit more about this longitudinal serial image data. They can become more and more available. And what we mean is simply every subject gets multiple scans. It's kind of intuitive, but it was not possible for a long time due to costs, scanning time, other reasons. But you see, you have heard about brain growth in pediatrics, where you follow subjects over time, aging, neurodegeneration, where you want to know for an individual subject what happens over time, trauma, for example, a baseline scan after the accident, and then after therapeutic intervention, how does it look like after 3 to 6 months? Or tumor growth. I'm sure you have heard a lot about that in this symposium series about staging of tumor growth and modeling. So you see, this data is available, but what we see in our community is the image analysis technology seems to lag a little bit behind. So we treat these images as if they would be three-dimensional images, but in fact we have repeated measurements of the same subject. So there is a correlation and a causality. So we should take that into account. So secondly, if you look at this clinical reasoning, if you go to the doctor, you see a lot of terms that we use, like development, degeneration, monitoring. They're dynamic processes, so these are terms in terms of the language of a time. So you see departure from typical development, delayed growth patterns, recovery of a patient relative to the baseline, prediction of onset, monitoring. So I just come up with this vocabulary and see if I see the doctor, they would always ask me, how was it last week? To predict how would it be next week. So that's the main motivation for our focus on longitudinal design of studies, but also longitudinal analysis of this data. Second, normative data. We heard a little bit about it also in Daniel Rückert's talk. We know the Gaussian bell curve. We know this is the mean and deviations, and we have percentiles. If we measure our blood pressure, we go into a chart, look it up and say, yeah, it's pretty normal, it's too high, too low. So I think we are used to normative curves. In pediatrics, you find these growth curves from the WHO here for circumference. You have curves for boys and girls. And when I talk to pediatricians, they tell me, we pretty like these normative models. And I see even parents go into this curve, they measure the head circumference, have the age, look it up and say, my child is in this percentile according to the norm curve. But you see something else too. You see this growth curve here which is pretty much kind of an exponential curve that has an asymptotic behavior. So I borrowed these slides actually from Xavier Pennek and Marco Lorenzi's research. This cross-sectional paradigm versus the longitudinal paradigm. So most often when we do clinical studies, we have a snapshot in time, and then we can compare two populations, normal versus disease, in a somehow time window. But if you look at disease progress, here you see time versus maybe atrophy, then you see there is kind of a dynamic process. So that means also only a snapshot in time might not give you the full information about the disease progress. And especially we see something else. If you measure a population, as we have seen in Daniel Rückert's images, there's a very high variability of a population, and the changes due to time is often very low. So the changes due to time is much often lower than the cross-sectional variability, as if you would measure all our brains here in this audience. And you can clearly see that here with an aging study. We have 50 subjects, 20 to 70 years, and I just sorted them by age. There is even one outlier. Now you can see, if you look at these images, you cannot really see the aging pattern because the cross-sectional variability is far too high. So if you do the opposite, somehow if you say we have repeated data sets, so repeated scans over time, and use that to measure trajectories of changes, and then look at the movies again. Now you see this aging pattern. So now you see what happens to all of us. So this is healthy aging, what we see in this movie. You see that the fluid spaces open up. Here, for example, the ventricular spaces, and also the Sylvian fissure. There is a deformation of the brain and also atrophy of gray and white matter. So you see, if you do spatiotemporal modeling, you get the information that you would like to have for the population and for the individual. So a few clinical driving problems that I want to address to show you some results. One is Huntington's disease. It's a genetic disorder. It's heritable. It affects individuals at kind of the middle age, and it's really a debilitating disease. So there is an NIH, National Institute of Health study, Predict HD, and we are kind of fortunate that we are part of that, to study the neurobiological progression of HD. So the way how we do that is there is longitudinal imaging, a few scans in intervals of 2 years, and then you see the main motivation is coded into these two graphs. You see here a motor exam score, so this is a clinical score, and the striatal volume, so putamen and caudate volume that you can measure from images. The red bar is actually the time of a most likely diagnosis. At that time, you really have a diagnosis of Huntington's. The blue box is the box of the time window. If there would be a therapy, this would be the time where an intervention makes most sense. If you do it here, it's just too late. So then you cannot. So somehow we have 10 to 15 years before the diagnosis that we would have time to intervene. And so you see, our research goes into the direction you have imaging, and you'd like to predict the timing, but also you'd like to predict in this inflection point in different data sets, could a therapeutic intervention actually makes a difference? So is there a change of this degeneration that you could inflict by a therapeutic procedure? Okay, you see the one baseline image of a Huntington's disease subject, then the follow-up after 1 year, and this is kind of a simple overlay with a kind of a difference measure, but you see the red region is the atrophy measure. So it's kind of a simplified version where what you see in brain scans if you do it over time on the same subjects and then you compare them. So another clinical driving problems which I like very much is also the infant age range. And you see there is really an amazing growth. So everybody who has a baby knows the first year is really amazing from 1 week to the other one. Now we go more to high-risk children. So high risk for mental illness. Based on heritage or heritability or a kind of a disease history. So we would like to understand the rate and variability in normal development. So we would like to have normative data, detect differences from typical, as I showed you before. And I think the notion is really the earlier the diagnosis, the earlier you can start the therapeutic intervention. Because they have a future, these kids, and some diseases are lifelong diseases. So in autism, we are involved in a longitudinal infant neuroimaging study. And this is kind of based on early findings. You see here the time axis at age 12. This is head circumference studies. At age 12, for the red curve, which are autistic subjects or subjects diagnosed with autism, there seems to be a change in brain growth. Whatever that means, that's actually the scientific question. You see, there is like an enlargement of the brain, or at least a process that makes the brain growing differently at early stages. So this kind of created the Autism Centers of Excellence project, again funded by NIH, IBIS, Infant Brain Imaging Study, where we do longitudinal studies across the US at 6 different sites with imaging, image processing, cognitive assessment. And you see some images here. You have seen similar images in Daniel Rickert's talk, but each child gets multiple scans. That's crucial. So we scan them at 6, 12, and 24. Now we scan them at 3, 9, and 15 as a kind of a longitudinal measure. We segment them, and you see here again imaging at 3 months, 6 months, 9 months, and 12 months. And you can see somehow the rapid changes. We have seen before the size changes, but there is not only size, there is also contrast changes in this early developmental pattern of brain development. Here I borrowed these slides from Daniel Rickert. You have seen that before. But you see this rapid growth in size and appearance that we can analyze. So we can also apply diffusion imaging, longitudinal diffusion imaging. I will get to the procedure just in the next slide. But you see this pattern of brain connectivity of a neonate, then the same subject at 1 year and the same subject at 2 years. And if you use these fancy technologies that you will see in the next 2 slides that computer graphics offers, you can actually study the brain connectivity in a so-called tractography style. Here the corpus callosum, which is the main connection between the left and the right hemisphere. But now look at the color coding in this slide. This is blue is less structured, red is highly structured. So if you look at the corpus callosum over time, you clearly see not only a size change, but a change of the maturation process. It's axonal myelination and pruning that's going on. So if you manage to register these data sets, we have heard this term registration before, you map them into the same coordinate system by nonlinear deformation, then you stick to some regions of interest, which are regions that are interesting for a clinician, and study the diffusion over time. So I have here the age axis and kind of the structuring index. You see you get these functions. This is a function of diffusion of the brain change over time. So diffusion, just a very simplified slide of this very complex imaging process. So would you put a blob of ink on Kleenex? You get this kind of beautiful isotropic diffusion. If you do the same on a newspaper, you get this kind of anisotropic diffusion. And this is just based on the fact that newspapers have cheaper paper quality and they contain fibers. So diffusion is most likely diffuse along fibers. And this is exactly what we mean by studying anisotropy. You want to kind of measure the difference between newspaper and Kleenex in that sense, but now you put it into the brain, so you want to measure brain tissue differences. There's actually Professor Le Bihan in 1984 had crucial research that actually made diffusion possible for imaging. So he developed these pulse sequences that could measure diffusion in different directions of an in vivo brain in 3 dimensions. And then together with Peter Besser at NIH, they developed technologies to calculate the tensor at each location based on these diffusion rates, and then map it into a brain image at every location, very highly sampled. And now what you can do is, if you look at structural anatomical images, you only see gray white matter. This is just one axial slice of the brain. But if you do diffusion imaging, it's striking how much more information that you get. It's just 5 minutes more time of a brain in the scanner, of a human brain in the scanner. Here the color coding actually means direction of the major fiber bundles. So you see left, right is red, anterior, posterior is green, and then inferior, superior in blue. Here again, in the cerebellum portion, where it's really striking that you start to see fiber bundles that come up from the spinal cord into the brain, just mapped by a new imaging technique. And if you give this data to computer scientists and graphics people, they actually map tensor fields. They're beautiful images in that sense, so they can visualize the tensors. And you start to see the deep structure of white matter diffusion rates. But then we can also do streamlined tractography. That means we follow these patterns locally from point to point and find the most likely paths to map the major fiber bundles of interest for clinical research. So one of the prerequisites for the analysis that I will show you is co-registration. Now we have different modalities of images. You've seen that before, anatomical images with different contrasts, but then also different ages. So we apply a mapping of all this data into a common coordinate frame, so age and modality. So all the images have now kind of the same coordinate space. And then you can kind of create regions of interest. So regions of interest that make sense anatomically and functionally, provided by clinical experts who provided this type of atlases for us. So we map these atlases with these definitions onto our data and get this data over time. So this is now age against diffusion rate for 8 different regions, as I plot here. The next step is statistical modeling. I have some more slides about that, where you apply a modeling of a parametric function that actually models this data for here 2 different structures that we see in the images, the anterior and the posterior limb of the internal capsule. Now you can see something which I want to emphasize in this modeling. We get the individual trajectories and we get the average trajectory, which is the fixed effect. So, because the emphasis is on individualized, personalized profiles. So with these techniques, you don't lose kind of the individual changes. You actually model them at the same time as you model the average trajectory. And I will show you quickly just with one simple equation. We used actually the Gompertz function. We tested statistically different growth functions. The Gompertz function has 3 major parameters. So it's a double exponential function. One is the asymptote, the other one delay, and then the growth or speed. And we also chose this function not because we like math or statistics, but the asymptote, delay, and speed have an intuitive meaning. So if you talk to clinicians and say, we found significant differences in delay, that already is a meaningful interpretation of the data that we hand over to the clinicians. Okay, so some other factor that we have to take into account is how do you do regression of longitudinal data? And we have already seen that foreshadowed in Daniel Rückert's talk. If you have longitudinal data, so we have 30 data points. This is a true measurement of diffusion in a specific region of an infant brain over time. You get this regression curve, and you may say, this is a pretty good regression in the least squares sense. However, if you do the modeling differently, if you know the red, green, and blue dots are actually the same subject measured over time. So you see now you get the trajectory for the red, green, and blue. So you measure the individual change trajectories at the same time as the average. And if you compare the regression without regard of repeated measures and the mixed effect modeling using a repeated measures model, you see these averages are quite different. It's actually striking. You may even say the left one is wrong because you did not consider that we have repeated data. So you did not put in the causality that we have. Okay, so now we applied this technique to autism study data. We have two populations here, high risk for autism, and for those who are not familiar, high risk means you have a sibling that is diagnosed with autism, and the risk for another sibling is 20 to 25%. So, and plus are the high-risk subjects that are diagnosed later with autism. Minus means negative diagnosis. So see the two curves. May I just grab some water? Thank you for allowing me this break. So the statistical analysis actually showed us we found a difference at 2 years of age. This is the time when you can think about the first diagnosis. You actually do it again at 3 years to confirm, but we also found differences at 6 months of age if you do this modeling, as if there would be an early biomarker for brains that develop autism later. And these first findings created a lot of attention in the community, because if you talk to parents who have autistic children, they're really desperate. They want to find a cure. They want to find better treatment for their kids. So you see, brain scans detect early signs of autism, or researchers see differences in autism as early as 6 months. So this is not just my work. We just created the technology, and a long list of clinical collaborators finally have put it together. So just an example how technology that we develop in this computational medicine make it into new clinical findings, which we will confirm with other groups worldwide in the future. So we can go a step further and say, yeah, longitudinal track-based modeling. So far I only looked at regions. Now we can also create fiber tracts, and they are sometimes closely associated with cognitive measurements. Our clinicians would say, yeah, there is a relationship between a specific track and the cognitive assessment of a patient. And then we parameterize these tracts by arc length. That's one possibility. We treat them as a ribbon model from one end to the other one, map it with length, and then put the diffusion measure on top of it, and we get the function of length versus diffusion measure. So you get one-dimensional functions that measure diffusion along the tracts. If you measure them as a function of age, neonates 1 and 2 years old, you see green, blue, red. You see a clear change due to development, maturation. And you can also plot it as a function here of age versus arc length versus diffusion measure, model it with the technology that I showed you, with a growth model, and then get statistical models. So the right curve here is a statistical model of a population of the diffusion along this tract for a population of kids. So the color code here is the variance. Now you see a spatiotemporal model of a specific fiber tract of interest as a normative model, and the use of it is shown here. We actually applied it to a rare disease, Krabbe's disease, which is a myelination storage disorder. So these children will die if they are not treated just after birth. So you see here the normative model, the red one, which is the spatiotemporal model of a fiber tract of interest. And the black one is the individual subject. This is the Krabbe's disease baby. We can cut this plot in the middle here at 0 and get the kind of a cross-section. And now you can see we still have to improve the modeling. So you see some wiggling, but I just show you where it goes. You see we get normative data here, mean, percentiles, and we get our baby with Krabbe's disease mapped into the same coordinate system and get the lookup. So it's no more only weight and length and head circumference. It's a kind of a brain diffusion model of a specific tract of interest. So this is the way how we see normative models can be used in clinical studies. So let's quickly switch the gear to shape analysis. And we have here this wonderful book by R.C. Thompson. And actually I got kind of notice of that only after I visited Nicola Ayache's group several times, because they always talked about Darcy Thompson. And this book is available online if people are. But Darcy very early talked about shape changes over time as a deformation process, as early as 1917, with some amazing concepts. Even the Gompertz function has several pages, and sometimes we reinvent the wheel and think we are the first ones in 2013, but math is all there, so, and wonderful math. Okay, so shape variability. So just a few notions. We talked about variability. I showed you the movies. And when I visited Daniel Rückert last time, I also went to the museum, Science Museum in London. It's really a wonderful place. I came across this box of phrenology heads. They're all faces, so they're all heads. But something was interesting. Number 54 is the bust of a scientist. So this is the one. I just zoom it up. So you can say maybe you all belong, if you believe in phrenology, which is a dead end, we all know, you may all look similar to this scientific or bust of the scientist. But it more shows you they all are heads, they all are humans, maybe similar ages, but they all show an amazing shape variability. So studying similarity, we can also go to twins. So we have twin data. So twins measured in the same way with scans. Here we look at the lateral ventricles, so the fluid spaces in the brain, map them side by side. Now you see the upper row are identical twin pairs, the lower row are non-identical twin pairs, and even visually from this set of images you see identical twins have an amazing similarity of shapes, not only of the face, as you usually see if you come across identical twins, but also of brain structures. So I didn't expect that, because these are fluid spaces, but the shape is very similar if you look at the pairs. Similarly, now we go to longitudinal, to the time. We have here one subject, A, at age 2 and 4, second subject at 2 and 4. So just two different infants at two different ages. We segmented out with techniques that we heard in the previous talk, the set of subcortical structures and ventricles. And now if you look at the cross-sectional, if you compare A at age 2 with B at age 2, I mean, if you look at the shapes, you can see there's this big difference in shapes. You would say they are very different. If you look at the time change, these are just 2 years of maturation. They look very similar. There is an aging process. They're a little bit bigger. The volume is bigger. But this is really striking, the difference across two different subjects versus the very subtle difference that we have over time. And this is actually our chance. That's why I showed you the movies before. Maybe pathology sometimes shows very subtle differences that we want to detect, whereas cross-sectional variability is often huge. So we can make advantage of that using longitudinal analysis. So that spawns off this work on four-dimensional shape modeling. You see here shapes over time. This is just the whole head structure. We have only discrete time points. We cannot call a patient back every week. It's too costly. It's non-ethical to do that. And secondly, it's just not doable. So what we want to do is we want to interpolate this data into a continuous model. We have an assumption. We use an assumption that growth and degeneration is smooth in time. So here we use a methodology where also Stanley Durleman, who is also sitting in the audience, was heavily involved, and Xavier Pennek in the INRIA team of Sophia Antipolis. A continuous flow of diffeomorphism. So you will see more here. I don't want to go into all this math. Some of you even know it better than I. But what you do is if you have a series of meshes over time of this cerebellum structure, you have the force vectors that you show here. This kind of the vectors that point from one shape to the other one. Then you create an acceleration field and then can also display it as a velocity pattern. But important is this time varying deformation function. So you deform in time step across the whole series. I show you that as a movie. It's more intuitive what happens. You see the acceleration of growth. And actually the vectors disappear because acceleration has a different sign based on positive or negative, and then a velocity field. So this is the technique that we can now apply. You see the whole series of measurements that we have magnetic resonance measurements. We apply segmentation of brain structures or subcortical structures or whatever clinicians are interested in, and we create these growth models for each individual. So here again for the left and right hemisphere and the cerebellum. So same procedure. You just say we have these 3 time points and we create a movie. It's a little bit more complex, but this is what it is. So our clinician actually liked it. They said, sometimes we want to look at an image, a measurement, at the time when we didn't see the patient. So interpolation helps them to say, how can I look at the patient when, or the subject, when it was 15 months? So you look at an interpolated data set. Okay, we do that for a whole population here, the autism study. And here again, I remind you, HR+, high risk for autism with positive diagnosis, high risk with no positive diagnosis after 2-3 years, and low risk. So low risk is 0.8%, so it's less than 1% the risk to have a child that develops autism, whereas these risk groups, there is a 20 to 25% chance. So now we have a new problem for statistical analysis, and this is work in progress where some of the groups I know are still working on. So if you compare a group A and B, you want to do a group testing and say, is it significant? But each time point is now a 4-dimensional shape movie. So that's kind of a new situation. It's not just the volume. We have a full 4-dimensional measurement of growth that we have to compare statistically. So we do some early, I can say, baby steps towards solving that mathematically and statistically by, for example, fixing the time and comparing to a reference. And then come up with modeling. This is now the average pattern. So the average for the HR+, HR-, LR-. This is brain growth for the 3 different categories. This is kind of the fixed effect, so the average patterns. And if you look at the velocity field, you may visually see some differences between the groups. And current work in progress is make that more scientifically by converting visual impressions into statistical results. Okay, Predict HD. I talked about Huntington's disease, a very similar project along the same line, imaging every year. And if you, maybe you close your eyes a little bit and do some blurring, you may see some very subtle changes. It's nearly not visible. Ventricles may get a little bit bigger, and the caudate, which is nearly invisible here, the gray structure, gets actually smaller. Okay, so we have the hypothesis of atrophied caudate and putamen, and we would like to apply longitudinal shape regression, as I showed you before. So we use the same methodology as I showed you for the infants, have these segmentations over time, create these longitudinal models. Here again, the color coding is the growth as a function of time. Actually, here you see the time also shown as a number of months. And then we can generate continuous measurements back. So you see amygdala volume, caudate, hippocampus, palate, and putamen. They all go down. You see a decrease in structures, whereas the ventricular volumes change. So you have atrophy of the brain that you can detect for each individual. So what we expect, if you have different populations, so we have here different clinical risk groups based on genetics. So this is based on genetics and Huntington disease. We have here the control group, healthy controls, low, medium, and high risk. That means kind of the time to onset. And for the controls, we expect to have a flat curve. We don't expect at the age range of 30 to 60, there is a significant difference that we see in brain structures, but we see these low, medium, and high risk groups. If you study the population, so all the data in a statistical scheme, so we can verify what the hypothesis would be. But our goal is subject-specific analysis. If a patient comes in, you can tell them in average, you would be part of that, but you want to have an individual growth profile. So we apply our statistical shape modeling to this database. You see here, patients with Huntington's have very different onset times that we study them. So it's not a disease that is only available or only is shown after 65 or 70 or in a late aging. It happens at different stages of your life. So the lines are actually the individualized, personalized profiles that we get for caudate volume. The dots are the volume measurements of the segmentation. So you see the dots wiggle a lot, whereas we get this continuous measurement after shape regression. So we could not get the results if you look at the volumes. The segmentation is not good enough. The segmentation is not precise enough. So if you look at the results after shape regression, you see the control group, low and medium here, and then the yearly rate of changes that we see. So for the controls, we have a very small change over 1 year. For the low and medium, we see what we expect. So this is the first step towards personalized, individualized trajectories of changes. And we could show by shape regression, we could significantly improve the results. Okay, and quickly looking at the movie, we see here a control subject and the Huntington's. Here the shape regression was extended to not only include shapes, but also images. So it's an image and shape regression. We may say there is a little bit of atrophy, but now we can also do the interpolation during the time where we have observed data, but then extrapolate. You see what happens in the future to predict how growth will change. And I showed you a movie here. So the red box is an extrapolation from 2 years to 10, far beyond where we have measurements. We see some artifacts coming up. We exaggerate a little bit, but these are prediction models that are becoming possible to show if the disease progresses as we observe it. It may be seen as what we see here in the extrapolated data. So finally, I come to the conclusion. I showed you spatiotemporal image and shape analysis. I think there is still a lot to do. So for PhD students among you, it's really a field that is not fully covered. You cannot say everything is done. I think nearly nothing is done so far, or we have some early steps. But so main take-home message is, if you have longitudinal data, I would say it's not wrong just to look at them separately, but the image processing or the results really benefit from a four-dimensional image analysis and four-dimensional modeling of the data. And to do is still, we do it purely based on imaging and geometry. We did not put in any physiological model or functional model, as you see Nicola Ayache and Peter Hunter's work. So that's really a major step that needs to be done. So I acknowledge my grant funding, mostly NIH, National Institute of Health in the US, my U-Star sponsors for my professorship, my colleagues at the Ski Institute, and finally also colleagues who helped to develop this whole systems that we developed based on math, numerical analysis, and especially Stanley Doleman at ICM PTA Salpêtrière and Xavier Pennec and Nicola Ayache. Thank you very much.